Ready to rock? Okay. So where we left off yesterday is looking at the Bronsted-Lowry theory for how acids and bases work. So talked about Arrhenius' theory of an acid yesterday, where he looks at these hydronium ions being responsible for acidic or basic properties. Today we're looking at the Bronsted-Lowry theory, and so both of these guys independently in like different parts of the continent come up with a theory of how acids and bases work. And rather than looking at what everybody else is looking at, they look at how acids and bases perform in a reaction, rather than just looking at their properties. You know, what do they taste like, what is their pH, all that kind of stuff. And so they look at how they react in a reaction, and what they come up with is, so according to the Bronsted-Lowry definition for an acid donates a proton to a water molecule. Now, when we're talking about a proton, because hydrogen has one lone electron in there, most of the time hydrogen is donating that electron, and so it's just going around as H+, which is essentially just a neutron and a proton, and so that's why we can say that it's a proton being donated. Oops, I don't know if any of that got that. So that's what we mean by donates a proton, is really we're talking about a hydrogen, but so acids donate a proton. So if we look at what's happening in terms of this reaction here, the hydrogen from hydrochloric acid is leaving and going here. So that means this was the acid, right? It donates its hydrogen to water to produce the hydronium. So acid, yeah, look at me all fancy putting stuff in. Okay, I don't have anything better to do with my life. And ammonia, so or bases, they accept a proton from water. So looking at the ammonia reaction, so ammonia in water, what happens is one of these, if we look at this as HOH, one of the hydrogens break off and get donated to so because ammonia is accepting a, thank you, because ammonia is accepting the proton, it is considered the base, while water would then be and obviously we end up with the hydroxide and the nitrate ion. Okay, so just to summarize then, again, look at me. Ooh, there it is. In the Bronsted-Lowry definition, water does not have to be a reactant. So for hydronium ions present in hydrochloric acid, they can react directly with ammonia molecules. And the reason for that is, like, strong acids, when we look at hydrochloric acid, for example, it would dissociate at pretty much 100% to create those hydronium ions. So there's no point of including water in that reaction. If I look at this in terms of what's happening here with that proton, where is the proton going? Is it moving from the hydronium to the ammonia, or the ammonia to the hydronium? Right. The hydrogen molecule is going from the hydronium molecule to the ammonia ion. And so based off of this Bronsted-Lowry definition, whoever donates the hydrogen ion is the acid, which makes sense because hydronium is an acidic molecule. And whatever receives it is the base, which makes sense as well because ammonium is a basic molecule. It's feeling really fancy. Okay. Good. Oh, don't make me mad. Alright. See, that's a swear under my breath type thing. I can't because of these people. Okay, so just kind of to summarize, according to the Bronsted-Lowry, a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. So a Bronsted-Lowry neutralization is the competition for protons that results in a proton being transferred from the strongest acid present to the strongest base present. And we'll look at how we can figure out, if I mixed a whole bunch of acids and bases together, what two would react and in what quantities, like going to what sort of equilibrium. That's what we're going to do once we've looked at the definitions for the Bronsted-Lowry acids and bases. And so the reaction, the reaction that we'll be figuring out is just looking at the proton transfer from one entity to another, or from the acid to the base. Okay, so that's the first two things you have to know is the different definitions here for acids and bases. So acids, proton donors, bases are proton acceptors. Looking at them, it's pretty easy to figure out which is the acid, which is the base, as long as you understand what the rule is. Good? Good, because I moved on. A substance, so now we're looking at this part of the Bronsted-Lowry definition explains a little bit better than the modified Arrhenius theory why substances can react as both an acid and a base. And so we have two names here that we're going to have to know. The first one is amphoteric, which is a chemical substance with the ability to react either as an acid or a base. So a chemical substance, that's kind of the key word. And there's two definitions, two words that look almost identical, amphoteric and amphiprotic. So amphoteric is a chemical substance with the ability to act as either an acid or a base. And in this example, I put these two examples here. We'll take a look at what is the actual amphoteric substance. So in the first example, what we have happening here is the hydrogen from hydrochloric acid is being donated to water. So that means hydrochloric acid is obviously the acid here, and water is the base. In the second reaction, what's happening is the hydrogen molecule actually leaves water. And so in this example, water is the acid, and ammonia, which again makes sense, is the base. And so in this example here, what is the chemical substance that's amphoteric? Water, right? So water is one. This should probably be a two-way directional arrow. Anybody know why? Why is the top one a one-way directional arrow and the bottom one is a two-way? So yeah, strong acid, right? Hydrochloric acid is a strong acid, so we have a one-way directional arrow. Ammonia is a weak base, so it has the two-way directional equilibrium arrows. Okay, so that's amphoteric. What you're more likely to see then is, oh, again, look at me. Ooh, I was like crazy this day. I couldn't figure that out on my own. Is what amphiprotic is. So more likely, kind of a more commonly seen thing, I guess, at least in terms of Chem 20, or sorry, Chem 30, is amphiprotic. So now, what this does is it describes an entity, so an ion or molecule, with the ability to either accept or donate a proton. The other one is a chemical substance. This is an entity which is considered an ion or a molecule. So here's my two examples. Oof. My first example here, so looking at not bicarbonate, carbonate ion. No. Hydrogen carbonate ion. Which of these is gaining, let's rephrase that. Which of these in the reactant side is the acid? Water or the hydrogen carbonate ion? How do you know? Right. the water is going to donate its, so it is the acid, and that means the bicarbonate ion, which makes sense, is the base. The other thing that could happen with this carbonate ion, hydrogen carbonate ion, sorry, is, now if I look at this reaction, I'm producing hydronium, which means that now the bicarbonate ion is the one donating its proton to water. So this is now acting as the acid, and water is the base. And so in this example, obviously, these guys are the amphiprotic substance. If I do look at these, this Kc equals 4.7 times 10 to the negative 11. And this Kc is equal to 2.2 times 10 to the negative 8 moles per liter. So if those are the equilibrium constants for each of those reactants, even though both of these reactions are happening when this molecule is in water, is this substance going to turn out to be basic or acidic when you actually did a pH test with it? Looking at those Kc values. So this is the Kc value for this reaction, right? This is the Kc value for this reaction. Is it going to be acidic or basic? Can't tell? No idea. What has the higher Kc value? The top one, right. So this substance is going to act basic because of a higher Kc value. Okay, so just kind of saying, so when bicarbonate ions are in an aqueous solution, what's a bicarbonate? There's no bi there. Bi what? So two. Ions are in, some react with water by acting as an acid, other react with water as acting as a base, but the number of ions reacting as a base is over 2,000 times more than the ones that are reacting as an acid, so therefore we have a basic solution, and that's just what those Kc values are telling me. And that's just reiterating what I said. Okay, so again. Now, the Bronsted-Lowry is still, the Bronsted-Lowry is still a theory for acids and bases, and the reason for that is it does not explain why substances want to donate a proton. It just says, this is what happens, we don't know why it does it. The other reason is it cannot always predict what reactions are going to happen and what is going to be produced in every single circumstances. In the circumstances that we look at in Chem 30, this is a good definition. There is another definition, right? So this would be like the Chem 20. If you look at the Arrhenius theory, this is Chem 30. Look at the Bronsted-Lowry, and then if you're going to university and doing anything with chemistry, you would look at the Lewis theory, which is talking about the gain and loss of electrons. Pretty much everything you learn in Chem 30 gets thrown out the window when you go to university. In case you're wondering. Okay. Yep. Okay, so according to Bronsted-Lowry concept, acid-base reactions involve a proton transfer. The reactions are universally reversible. not necessarily always the case with our strong acids or strong bases, but we can, I guess, make it precipitate, at least with the bases. And they always result in an acid-base equilibrium reaction. So universally reversible, and they result in an acid-base equilibrium reaction. So when we look at these reactions, get out of here thing. So when I look at this reaction here, if I take acetic acid, so vinegar, and I put it in water, some of those vinegar acetic acid molecules will react with the water to produce hydronium, giving me that acidic pH and the acetate molecule. So if I'm looking at the reaction and I'm going in this direction, here I have this hydrogen, right, is donating here, which means the acetic acid is the acid, and the water is then the base. If I'm coming this way now, because these reactions are reversible, so now these would be the reactants. What's happening on this side is the hydronium is reacting with the acetate ion. And so the hydrogen is being donated now from here. One of these guys is getting donated to here, so hydrogen, if I'm proceeding from the left to the right. And so now this is the acid, and the acetate ion is the base in this example, if I'm going in the reverse direction. So those, if I'm looking at, what did I do this for? I'm actually not myself for this and time doing this. Okay, so when I was looking at this, and so we said this donates to here, and this was the acid, this was the base, and then I said this comes from here to here, this was the acid, then hydrogen, this is the base. We have what's called conjugate acid-base pairs, and conjugate acid-base pairs are, where's my ink color? It's a different color, whatever. They differ only by a proton. So they're molecules or entities that differ only by a proton. So they differ by a single hydrogen. And so in this example, these two are what we would call conjugate acid-base pairs, and these two are then my other. Don't listen to my spelling. Conjugate acid-base pairs. Where's my ice? We'll look at later how to figure out which of these reactions would be stronger. Like, would it be stronger to be going this way? Or would it be stronger to be going this way? Like, what side of the reactants is favored? That's what we're gonna look at. And obviously, anybody know like what reaction is favored? What was I doing with my life? So the ability of the acetate molecule to keep its proton is much greater than the water to attract it away, which means that the acetate ion is a stronger base than hydroxide. So we should be favoring my products. No, sorry, reactants. But we'll look at how to, we have like a, kind of like a redox type table, like this compared to this is what we're going to look at. Is this stronger than this? Spontaneous, not spontaneous, but in this case, we'll look at reaction percentage. Oh, that's that. Again, I don't know what I was doing. Okay, so just a few pieces of information here. So a strong acid has a weak attraction for protons. So the top 6 acids here, hydroiodic acid, hydrochloric acid, sulfuric acid, nitric acid, all of those acids, what they really want to do is get rid of their protons. They don't want them, they want to get rid of them. So that's why we get those acidic properties, because when they react with water, the water gains the hydrogen, creating that hydronium. A strong base has a very strong attraction for protons. So looking at like sodium hydroxide, that OH ion has a very strong attraction for protons, so it takes it away from the water, and we get those basic properties as the hydroxide. The stronger an acid, the more weakly it holds a proton. So like I just said, the stronger an acid, the weaker its conjugate base. So in that, if I'm looking at like, let's say, if I had a strong acid, like hydrochloric acid, that's the acid. Its conjugate base would be what? Does anybody know? It would be a chlorine ion, right? So chlorine ions are a weak base, and hydrochloric acids are a strong acid. The stronger a base, the weaker its conjugate. So that's a harder one. The stronger a base, what do I want to do? Let's go with NH3. So NH3, if that's a strong base, its conjugate acid would be what? NH4 plus, yeah. Why is it NH4 plus and not like NH2? It needs to be able to donate it, but NH2 is not something that we know as an ion that's like existing. We know ammonia and ammonia exist, right? So we're always we're not just creating a random molecule, it's always something that we should know. I don't know. Alright, just lastly, some general rules. HA here, it just stands for a weak acid. So when a weak acid reacts with water, we'll be producing hydronium and then some sort of anion, and which would mean these two are conjugates. Come on, why don't you like me when I'm writing? Oh, I'm touching down there. So a weak base holds its protons weakly, but it holds it less weakly than a strong acid, if that makes sense. But they will still easily lose their proton to any base that's present. Conjugate acid strength must be very weak. And I think I wrote that down. You don't just have to. The stronger an acid, the weaker its conjugate base. The weaker an acid, the stronger its conjugate base, which is repetitive. I already wrote that down. And then the chart on the bottom of your note page, we'll look at that tomorrow. And by tomorrow, I mean on Monday. Monday. Okay.
Monday.
Be here, be square Monday, friends. We're doing homework. Let me see. So in the homework book, homework 6.